We'll have a quiz on everything that I said in the first few minutes. Okay. My name is Axel Floth. I'm the CEO and founder of a company named Abacus Semiconductor Corporation. We focus on building, designing, engineering processors for AI and include into that the accelerators that do all of the heavy lifting, plus smart memories, because it doesn't work without them properly. We've heard a lot about AI today, and while it's all fantastic, today most AI, if you look at the training part, runs on GPUs, and they were never intended to be the central part that does the heavy lifting and the math for AI. So needless to say, they are not the most efficient and effective ways to do that. There are many other ways. There are companies, first, second, third generation of AI chips that do the acceleration for all of that. But again, we're going also back to the first talk from today when we heard about the system think instead of the component think. And so that's what we're going to go through today. And then also have a look at what AI needs to run properly, because AI in the end really is just a whole lot of not quite trivial math, but in the end it's tensor math. So it's you take a multiply between two different vectors, right? It's one vector, a column multiplied by a row. And that's really all that there is, except for those data sets are incredibly big. And so therefore, there are certain things that we need to be able to fulfill in hardware to make the AI software, at least for training, run properly. And properly meaning fast and with the least amount of energy that we can spend to do that, because we can't get below a certain threshold, because that's the information theory that will prevent us from going any lower than that. But we don't really have to waste that much energy. And the biggest problem that we're facing, and it's of course called LLMs for large language model, the AI input data sets are incredibly large. And we're not talking gigabytes, we're talking tens or hundreds of petabytes worth of data. And that data needs to be made available to the processors and accelerators so that they can crunch it all and combine it into what usually would be called a foundational model. And that foundational model is then used by the ChatGPT prompt engineers, and that part is called the inference part. So there's the training part, which operates on incredibly large data sets, and then there's the inference part, which luckily doesn't have to operate on data sets that are as large as the one for training. And that means, of course, that if you want to train something and you want to use your own data, well, you better have a computer or a set of computers, a data center that provides you with the memory, both on disk for mass storage and on main memory, so that the processors and the accelerators can access it to work on this data set to crunch it, right? So the foundation is having access to very large memory that ideally is coherent. And to explain that a little bit, and I assume we don't have a lot of computer scientists in here, imagine you've got something where 100 people have to collaborate, right? And in that case, you want to have the 100 people around a centralized thing that you share the data through and with, but everybody has his or her own desk, because there's certain stuff you need to work on once you've picked it up from the desk. And when you're done, you put it back onto the desk, right? What you want to avoid is a situation in which you work on data that's already outdated. So let's say somebody put his work results back onto the desk that now needs to be flagged. This is being processed. Don't touch, it's done, right? Because if you touch it and you think it's your input data, the original one, well, guess what? Then you already work on the data set and invalidate everything, because you've already taken an interim result and worked on that with an algorithm that shouldn't have been used on it, right? So that's coherency. You need to be able to distinguish what has been worked on, what is being worked on right now, and what you can take to work on individually. So shared memory, the centralized repository in the center, right? and then your exclusive workspace where you can do your own work any way, form, or shape you want. So that's, in general terms, how it works, for layman's explanation, right? And so that means that if you want to use a computer or a data center for AI, particularly for the training part, you need very, very large memory arrays. And they need to be capable of notifying the other workers when something has been worked on and when something is being worked on, or if it's available to be worked on without messing anything up, right? So AI training requires very large-scale memory that is coherent. And that's not easy to implement. We've done it, we know how to do it, and we've done it properly with the least amount of energy expense than compared to the traditional methods. Now, if you want to do the work on it, well, guess what? You also need the workers, right? And the workers in these cases are the accelerators. And for the most part, because the training part of AI is vector, matrix, and tensor math, you need accelerators that can do this work. It's foundational to AI to create a model through these particular math functions. And the faster your accelerator is and can work on something that looks like matrix or vector or tensor, and the more energy efficient it is, the better your accelerator is, meaning you're done with that task faster at less consumption of energy, primary energy, which also means you don't need quite as much cooling as the traditional methods do, right? Because again, if you feed power in, guess what? Out comes heat, right? That's just the nature of the beast, right? So the next thing you need to be able to do is distribute the tasks, right? Because if you've got 100 people sit around a table, the people will be willing, capable, and more than able to do the work and to figure out who's doing the work and who's doing what. In computer systems, that's not quite the case. So you have to have an entity somewhere that distributes the task and say, you do this, and when you're done, you put it all back, right? And so the distribution of the workloads is another crucial element that you have to make a supercomputer that crunches your AI data, right? If you don't have that, then it becomes a whole lot less efficient, instruction efficient and energy efficient. And of course, we want to avoid that because nobody can afford to build a nuclear power plant right next to the data center. That's not going to happen, right? The permit process alone is like 25 years. Right. So what have we learned so far? Data should be shareable, high-level instructions should be shareable, and we should have access to very large memory. And today it's all done, pretty much everything is done with what is called a GPGPU, a general purpose graphics processing unit. And as the name implies, it's very good at doing graphics processing. It's not necessarily very good at doing other things, but we're basically, the industry is using GPGPUs today because they have a high level of parallelism. If you buy a processor, you get 64 cores. 64 cores really don't do much difference in the crunching of the data size if you assume it's hundreds of petabytes worth of data. So the benefit of a GPU is that they are very, very parallel. You can get 8,000 to 9,000 single render cores in a single GPU. And so now, while they're not as flexible as a CPU, at least you have 9,000 devices instead of 64, right? So that's a huge benefit, and that's why people today use GPUs to solve the AI crunching problem for training, right? Not ideal, but it's workable. So we need lots and lots of those cores to crunch the data. The problem now is that when you've got lots and lots of cores, they have to be able to talk to each other. And if you do that on a single die, it's doable. I mean, it's stretching the limits of what we can do, and not only in implementation and engineering, but it stretches the limits of physics, because the fact that they have to, or the electrical signals have to traverse a network of interconnects between one element and another element, we're finding that light is just too damn slow, okay? And there's nothing we can do to speed that up. Light isn't going to be any faster anywhere else, right? In vacuum, it's 3 times 10 to the power of 8 meters per second, roughly, right? There's nothing we can do to speed it up. So what can we do instead? We can figure out a way to make the interconnect such that the latency to get from A to B is pretty much only dependent on the net delay and not on all the other stuff that we're adding on top of it. And unfortunately, in computer history, things rarely ever get thrown out. There's always more and more to be piled up. And so you can imagine the more layers of stuff you have to go through, the higher the latency, which means your round trip delay gets bigger and bigger and bigger. And that's the opposite of what we want. We want the latency at the round trip time to be as low as we can. And unfortunately, as I said, in computer engineering, we have no system view. We have a component view. And everybody responsible for one of the components says, well, but that component is necessary. We need this. We can't take it out. And again, the more you pile up, the worse it gets instead of better, right? And so that's one of the reasons why we have decided to completely rethink everything and throw everything out we didn't think we needed, and then saw if it still works. And if we broke it, well, okay, well, we'll put it back in, right? But for the most part, we found there was nothing we had to put back in. We just split the architecture differently. And I'll come to that. There are a bunch of schematics later on. Right? I just wanted to make sure we all have the same understanding of why we do what we did and what the implications are. Right? So, and then of course, it's not only one single processor that crunches it, it's hundreds or thousands or tens of thousands of servers in the data center today, each one of them with a CPU and a GPGPU. And now you have to not only communicate on the chip for the processor itself and on the chip of the GPU itself, you now have to communicate between each processor and each GPGPU. Well, that wasn't ever intended to be that way, ever. And so we, again, have thrown out as much as we can to make sure that that latency from any core, be it a processor core to any other core, could be a processor core or an accelerator core, is minimized with simultaneous fastest possible access to shared memory, because as we just discussed, the data and the meta instructions have to be in shared memory for it to work, so that processors and accelerators can fetch the data they need, work on it, put it back. Now, ideally we want, of course, linear scaling, but that's due to the fact that photons are too damn slow, not possible. So scaling will always be near linear because, again, the communication between cores is predicated on the network delay. And the more distant the units are and the devices are that have to be involved in the communication between them, the larger the net delay. So we have to plan for a relatively large net delay if we communicate across processors and accelerators. On the die, we know exactly what the distances are, so we can optimize that for clock frequency. Off die, we have to have a look how we manage the minimization of latency between any two units, and that's what we focused on. And of course, the more linear we get, the better performance we get at the same power consumption, or conversely, if your performance goal is static, then we drop the power consumption because we are simply more efficient and effective. We don't have the cores waiting for communication, for interprocessor communication, and for the round trip delay to be ready for a message to come back, right? And so that's why, again, our main focus was on reducing the latency, meaning the round trip time between any two units, and that enables us to improve on the performance per watt, meaning that in a data center that is not directly located next to a power plant, a nuclear power plant, we have a performance or power or both advantage over existing solutions. And that means, of course, that also trends that we've seen lately, like rehoming or repatriation, can be supported, because if you are a hyperscaler like Google or Amazon, then yes, you can build your data center right next to a nuclear power plant, not a problem. But if you're not an Amazon, and if you rehome your IT, you're bound by the limitations of the power you can get to that plant and the ability to cool, right? And the rehoming trend, Gartner says 47% of all companies want to rehome, at least crucial IT. That leads to the fact that they are much more focused on energy efficiency and destruction efficiency. So this is a little bit of computer science here, and this is our solution to the problem, and that's called a beyond hardware architecture. If you look at a traditional processor, you will always see the general purpose input, general purpose output. You've got the CPU core, and the only thing you see here are not those three boxes that I call your I-cache, D-cache, and scale-out port. The only box here that you see is going to be the memory, because any processor needs memory, right? You always have interim results that you have to put somewhere that don't fit in the registers, so you put it in the memory, you fish it from memory. And that was how computers started out a long time ago, a very long time ago. Exactly, fundamental architecture was von Neumann, right? So now, von Neumann worked for as long as processors were slow and memory was slow. Not a problem, right? And then memory became denser but not faster, and processors became faster. So now we had to do something called caching, meaning we use fast memory to take data in and out that we can't put into slow memory yet because the slow memory is too slow. And then we dump it from the fast memory to slow memory. Or if we need to have access in read direction, well, if one instruction or one thing gets read, we read more than necessary. We put into a cache so that it's available for the processor to fetch right after the next access. And that worked out reasonably well for as long as the processor kept getting faster and faster, and the memory kept getting denser and denser and not faster. It completely collapsed when we started building data centers with tens of thousands of processors, because guess what? Now the interconnect between processors and accelerators had to go through general purpose I/O, and that's slow. And we don't want slow, right? Whether we drive or do anything, we don't want slow, right? Particularly latency, delay, right? That's the worst enemy. So we came up with the scale-out port on top of the I-cache and the D-cache as the third port on a processor or accelerator core. And that's the foundation of our patent, right? That now allows us to directly connect processor cores to accelerator cores and also to memory, particularly smart memory. And now we have the ability to have many, many processors and many, many accelerators work on a shared data set that is in one or more smart memories. So we have achieved the latency reduction, we have achieved the integration and seamless integration of processor and accelerator cores, and we have achieved not only the communication, but also direct access to smart and fast memory off the scale-out port. Right? That is the secret behind the patent. And while doing that, we can now build a processor or a server with processors and accelerators where we are directly interconnecting all of that stuff. And I'm just saying stuff because it really is in the end stuff. So we've got a CPU core, we've got an integrated switch, yet another integrated switch, another core, we can connect them directly. We don't need a switch in between because the switch is already part of the processor or the accelerator. Again, reducing latency. So now we can get from processor core to processor core on the die with minimum latency, and we can do the same across the accelerators, and we can do that from processor to accelerator and to memory. And if we make the memory smart, it allows us to directly tag all of those entries that have already been processed. So the processor and accelerator doesn't have to do it anymore. The memory does it. And that again reduces latency and improves our ability to share data across anything that there is that has access to that shared data, be it data, the input data, remember, petabytes, hundreds of petabytes worth, and the meta instructions that we need to tell the accelerators what to do. And once you attach smart memory to it, you have now the ability to directly share that, even if this needs data from here, because they can signal, hey, look, send me this, I need this. And now this CPU core or accelerator core doesn't have to do any transfer in software. It does it in hardware. It requests it, the data comes, and there it is. And that, again, dramatic reduction of latency, which again helps us in the goal to have many, many processor cores and accelerator cores work on a shared problem, particularly if it's at the size of the input data we typically see in the training of a model. And that is the foundational and fundamental advantage over what's out there today. And as you can see, because of the fact that this is integrated here, the switch, there is no need for a switch in between, an external switch, which is what is today's industry standard. So industry standard today, that's what it looks like. And that's a very traditional setup of a server. So your server, effectively today, looks like this. You got a CPU, you got a PCIe root complex, which is how you connect peripherals to a CPU, which of course should be the first indication that this is not an ideal solution, because an accelerator is not a peripheral, right? It's an accelerator that should be on the same level of hierarchy of importance in the CPU core, right? So again, CPU to the root complex, and then to a device controller, PCIe device, then to the GPGPU. It has its own memory, but this is not smart memory. So this can't transfer anything by itself. This, let's say, the data you need is in here, it needs to go in there, but the CPU has to initiate a transfer and push it out there. And PCIe, unfortunately, has a sliding window of very, very small size, 64K. Yes?
Yeah, I was just wondering, how would you compare this architecture that you put together with servers?
Oh, very good question. So the question was how I would compare what we did with Cerebras. So Cerebras is a company that built a second generation AI accelerator. And what they do is what they call a wafer scale engine. So they put hundreds of thousands of processors on a single die, right? That is an incredible engineering feat, which also makes it incredibly expensive because they need lots of redundancies, and they still have the problem of the net delay determining the round trip time, right? And so their solution is always predicated on the longest possible round trip time that they can think of for an any-to-any communication. And by doing that, that delay is incredibly high, right? So if there's inter-processor communication with a handshake needed between any two entities, they have to account for the largest diagonal. And that's not a pretty picture. So while it's an engineering feat, it's not really an advance in the architecture of a processor or accelerator because it doesn't have a scale-out port, for example, right? So they don't have a direct way to connect a processor core to an accelerator core. They're either all accelerator cores or CPU cores, right? That's unfortunately the way it works, right? So we overcome this. And if you look at this, this is one server, and you've already seen how inconvenient it is to get data from here to there. But now imagine even worse, they are in two different servers, right? So now you have to go through what is called a top of the rack switch. So the top of the rack switch would then transfer all of this to this one or to this. And now NVIDIA had thought about the idea of, oh, what do we do if we just circumvent the entire spectacle of the CPU? So what they have now invented is called NVLink, the NVIDIA link. And that is effectively an overlay network that goes from the GPU to an NVLink switch, and then to another GPU. So now the teeny tiny problem is you will create race problems. Imagine this data from here needs to go here. Guess what? The CPU says, oh, look, data was fetched. So it's not exclusive, and it may have been modified. The CPU has transferred that over and copied it to the GPU memory. And the GPU now says, oh, okay, this is new data, and I may have to share it. So it's not exclusive, it's shared, not exclusive, and I don't know if anybody has modified it. So now what happens is, the CPU will send a notification, hey, there's something that may have been modified, don't work on it, right? And so does this. So the same information arrives twice here. And now you don't really know, okay, what happened? Am I still valid? Should I work on it? Or has the race condition destroyed everything that looks like coherency? And now the software has to kick in and say, well, let's have a look.
5-minute warning.
Yep. Okay. So the problem with an overlay network is very simply, yes, on certain applications you accelerate, on most applications you just create more headaches, right? And so that's the current state of the art. We think we're a little bit better than that, right? And that today is how foundational models are created from the input data by crunching them. And again, most of the math is matrix, tensor, vector math. It's not rocket science, really. Everybody has known how to do that properly. But the main issue always has been how to make sure that all the processors and accelerators have access to shared memory so that the data can be crunched, right? That always has been the problem. I think we solved it better than this. A lot of people ask me about the inference part, and I've already pointed out, yes.
Yeah, so just to kind of quantify, so sure, you have a better architecture,
Yes.
but is it like 2 times faster, 50% faster?
Well, again, we are at near linear growth, whereas NVIDIA is at logarithmic. It can be anything from like 0 difference to a factor of 10, right? And on very large installations can even be bigger than a factor of 10, right? But this is, again, this is targeted towards the training part, not inference. Inference is different. It doesn't quite need as much compute. So inference is what you can even do on your cell phone, theoretically. It doesn't really compute much there, right? So that's doable. And therefore, we have focused on the training part, not the inference part. Now, agentic AI, again, is different. And I copied the definition of agentic AI from, I think, the Britannica. And so this is a reasonably good explanation and definition of agentic AI, but in either case, you need a lot of math in the training part, whether it's agentic AI or just the LLM type training, doesn't matter much. It's in fact the same math. The only thing that is maybe a little less are the sum of the transformers, right? Other than that, there's mathematically no difference. They all use the same math. It's not a big difference, right? And so that's why we believe what we have is a lot more effective and efficient with regards to performance and power than anything that's out there, because again, we didn't have to be backwards compatible. We had to look at everything that we could throw out. And I'm very good at throwing things out, believe me. My team loves me for that. So that's what a server would look like if you build an accelerated server out of our stuff. So you've got the direct interconnects, as you can see, and you've got all the connections directly to the accelerator, a seamless integration. And on top of that, You can do optical to electrical conversion here, so you can go from mainboard to mainboard optically. And by doing that, again, this is a point-to-point connection. Therefore, we don't need an external switch. So it doesn't have to go from the server to the top of the rack switch and then back to another server. It goes directly server to server. And that's another advantage where, again, we have much more latency, much lower latency. Okay, I think I'm maybe out of time. So if you've got any questions, let me know. Any other questions, I'd be happy to answer them. And, yeah,
Not Q&A portion right now, panel portion.
Okay.
All right, so can we have all the panelists, Stephanie?
Okay.
I'm gonna go grab everyone from the other room.
Okay.
We're gonna do something fun. Everyone get up.
That's how you get a standing ovation. Tell them to stand.
No, TSMC. We design and engineer and manufacture. The fab these days is $25 billion.
Yes.
You don't want to blow those out. We have a partner fab.
I can't find it.
You can't find yours?
Yeah.
I was trying. He's just over there.
Yeah.
Okay, great.
All I
Come
ask
on
you,
over,
count
everyone.
the number of units in between A and B for your output, right? So you see what you're.
Can we start?
Yeah.
Yeah.
Okay, so 1, 2, 3. Is there a third person? Oh, Drew. Drew is supposed to be
Drew,
the third person.
We're okay.
I think it'll be all right.
He's gonna be part of it. Everyone's gonna be part of it. Yeah.
All right, where are we going?
Okay, everyone come into the,
All right, everyone.
Middle.
Our panel on the semiconductors is about to start.
okay.
All right.
Front row, back row, doesn't matter.
Yeah, I will explain it. Everyone just come on over. Okay, my name is Stephanie Miller. I am an independent consultant. I got into tech this year, and I'm a COO of an ethical AI company called Fondue. And I'm also working with a
Use the
legacy
microphone.
materials, working with a legacy materials solutions company in friction materials for brakes and clutches, supporting robotics lately. So I'm working on the GTM for that. So it's really exciting stuff, and I'm so happy to be here. Dwayne, thank you for this opportunity. I recognize a lot of familiar faces, and it's nice meeting many new ones. And what I'm really excited to talk about, this is all really new to me, semiconductors, but I love learning, just like I think all of us do here collectively. And as I'm learning more about it, one of the things that I can connect it to in a past career of mine in environmental consulting is energy savings and how we're all really working together. And I remember getting into tech thinking that AI is just, or the cloud is just another world. And so with that introduction, I would like to pass it on to Alex. He can do his
Is there a
own
reason
introduction.
You guys are standing?
You want us to
Yeah.
stand?
Yeah, and then we're gonna do a really fun.
She has a plan.
I have a plan.
All right.
So I'll let Alex introduce himself, and then I will tell you how we're all gonna participate.
Hi, folks. My name is Alex Horvitz. I am the VP of Manufacturing Operations at a company called Snowcap Compute. We recently got funding to get out there and build some different style digital computers. So we're very aggressively tackling the energy problem. And we have a new
Must
way
be
of
popular.
yeah, a new way of approaching the problems that traditional semiconductors have, but we'll still be providing digital compute in a quantum adjacent space.
Yeah, what can I say? Physicists, computer scientists by training like to take things apart. Oftentimes I get them put back together properly. Sometimes I don't. Most times when I put them back together, they work better than they did before. And I think we did that here too. So, and of course, we also had a very close look, in fact, at cybersecurity issues. So, for example, attacks like Rowhammer won't work on our architecture because they're fundamentally blocked out.
Thank you. Thank you both for being here. What we're going to do, show of hands, who has been here all day? Keep your hand raised if you were also here yesterday. That's amazing, amazing.
Stamina.
It's a lot of stamina.
No sleep, no food.
So what we're going to do for this panel is.
Gift card?
Pardon me?
You got a gift card?
You got a gift card.
Check under the seat.
Oprah.
Yes, you get a gift card in here. So what we're going to do is an activity called Four Corners. If anyone's familiar with it, we're going to start with absolutely agree in this corner here with a statement that I'm going to say. If you absolutely agree, come move your body over here. If you slightly agree, you're going to be in this corner, slightly disagree, and absolutely disagree here. And then what I'm going to make this statement. We're all going to move, and then our panelists are going to give us some deep insights. And we'll see if that changes any of our perspectives or if it reinforces our perspectives, and then we'll give everyone an opportunity, maybe one or two on each of our questions to participate as well.
Here we go.
Here we go. First question. Most companies aren't ready for on-site premise AI hardware. Absolutely agree. Slightly agree.
Most.
Or mostly.
Most companies.
Most companies.
Undefined company.
Okay, and then this, for the purposes of what we're trying to do here, it's however you want to interpret it. So we won't be too technical on the question. It's, okay. So, agree? Okay.
Mostly agree.
I agree, and I think I've talked to probably about 200 customers in the last 8 months, and everybody says, yes, we want to rehome and repatriate, but we're not ready. We don't have the personnel, we don't have the talent in general, we don't even have the building, and we haven't even ordered the servers. So they all say, yes, we want to do it, but 3 to 5 years timeline.
Yeah, I'm not going to get me to disagree with that. I think the wonderful thing about cloud versus on-prem is if you've been around long enough, I have gray hair, you remember that we go through cycles, right? For a while, everybody wants to be in the cloud because Amazon was offering it was super cheap. Then it got a little expensive. People were like, we should rehome it. And then, Microsoft came online and Oracle tried to make other clouds. And like, oh, it's competitive pricing, we'll go back to the cloud. And it seems like we're in a spot today where people have forgotten what a pain in the ass it is to run their servers on-prem, but we're also in a security situation where it's probably smarter to run your services on-prem. So we probably have to figure it out.
Anyone absolutely want to share from either group? Or shall I move to the next question?
Well, electricity and cooling as well. I don't know, does it take more? Are they not prepared there too? Or is it just getting them, the boulder behind the boulder behind the boulder?
Well, so yes and no.
Okay.
If you go for the traditional architectures, your cost will be, of course, higher in your on-prem because the hyperscalers have much more capability to negotiate with the prices of electricity, right? So usually they're at about 5 to 7 cents a kilowatt hour. If you're in California and you're very, very lucky, you pay 12 cents a kilowatt hour. 12 cents a kilowatt hour means that 1 megawatt will cost you $1 million a year, right? And 1 megawatt these days with the latest racks from NVIDIA, well, that's 8 racks. 8 racks is a megawatt is $1 million.
So on my end of it, my company is working very hard to bring that down. So we would be about 0.1 megawatt for 0.1 for 10, roughly. Or let's just do gigawatts because I know Axel likes gigawatts better. So 10 megawatts per gigawatt. And we only need about 15,000 square feet to run a gigawatt data center, including all our cooling infrastructure.
So is the power the only factor that's dictating whether they, is the power the only factor that is dictating whether they could own on-prem or not? Or is there other kind of factors, economic factors like scale that comes into picture?
So I think there are many, many factors that factor into that, or many, many reasons that factor into the decision. Because again, will a hyperscaler have better prices on power? Yes. will a hyperscaler be able to utilize more servers per admin personnel? Yes. So the average price should be lower than your on-prem, but the problems that arise is that oftentimes you're limited by data security and data sovereignty issues, right? So data sovereignty may mean that you can't just harvest all data that there is, including from your competitors and possibly other nations, and then take that as your foundational model for your training set. You can't do that, right? That's a legal issue. So you've got legal issues, you've got cost issues, but what most people didn't think about when they moved to the cloud was that the cloud really is the exact same servers in the exact same racks, managed by people with the exact same skill set, but you still had to have people that managed your particular software and the configuration thereof, right? So that really didn't make a difference because your requirements for the software that you needed were the same for the cloud and for on-prem. So the only savings on the cloud versus on-prem were cheaper power and fewer administrators per server that the hyperscalers just simply stretched out much thinner.
Yeah. So this conference has kind of a blockchain side. So Axel, to your point about data sovereignty, I think in the enterprise is very much focused on privacy, security, and confidentiality, which the hyperscalers do not provide and are going to provide less and less moving forward. So there need to be solutions that are cheaper and faster. We're big fans of small language models rather than large language models, which can be run, a lot cheaper, a lot faster. They can be fine-tuned for the enterprise. They can use their own data, not worry. They can have, data sovereignty. So I think there's going to be there's a mismatch right now between what's available and what the enterprise wants. If the enterprise can get what it wants, then there will be a shift back to probably on-prem for data security and data sovereignty issues.
Last question.
Okay, thank you guys. Quick question though. I remember the on-prem days. You also have to have redundancy. You're an earthquake country or fire country or flood country or whatever. So are those costs that you're talking about? Does that mean you're also, why first rule of government spending? Why have one when you can get two for twice the price? So are you doing it twice, or is there an intermittent backup? And then the other question is for if you're doing the service model, did your prices that you were quoting include their redundancy?
Yeah, again, multiple questions, multiple answers. So redundancy and resilience can be achieved two ways. One is, of course, you can make each one of the servers pretty much impermeable to any kind of accident that there may be. That's a fairly dangerous thing. I don't believe in it. I believe in making it as secure as you can at a fixed price. It doesn't matter or it doesn't make any sense to build $1 million server when you can do it for $100,000, right? It doesn't make sense if you gain 3 or 5% of resilience or reliability out of it. That's pretty much it. But again, the cybersecurity aspect of that is the more data centers you have, even if they're distributed, the larger your attack surface is.
So we have a view of, our chief scientists and our CTO wrote a paper that you can find at IMEX online toolkit about putting a data center in a shoebox, right? So we can put a data center in a shoebox, but you imagine that's 3 cubic feet. We have about 47 cubic feet or 37 cubic feet to cool, right? It's cooling infrastructure.
Yep.
But that conveniently fits in a 40-foot shipping container. So our proposed solution to the problem of needing redundancy is essentially, buy 2 shipping containers, and that will give you redundancy, and you can have it come online as needed. It would be difficult to attack our infrastructure. It's being cooled by liquid helium. So if you want to get in there and mess with it, that's your business. But we feel like we would know if there was intrusion well ahead of you being able to do anything useful. So,
It's an interesting question.
We're gonna do one more, and then here we go. GPUs, yes,
Are we doing, you mean one more?
one more move. Ready? Everyone up. Let's do it. Okay. GPUs will be replaced by specialized AI chips within 5 years. What do you guys think? I'll read it again. GPUs will be replaced by specialized AI chips within 5 years.
That's an absolute statement.
Is that-
You're making an absolute statement.
Absolutely.
Absolutely agree.
Absolutely agree.
Yeah.
Slightly agree,
Disagree.
slightly agree, slightly disagree, and then absolutely disagree.
Does that mean Axel's standing, are you just
No,
on
no,
stage or are you in slide?
No,
No.
I'm saying, I don't count, I don't count.
Or mostly.
Mostly agree.
I should have written them on the.
Yeah, so there's a very simple precedent for it, right? Because Bitcoin mining 5 to 7 years ago was all done on GPUs, 100%. And now it's exactly 0% because the specialized ASICs are simply more instruction and energy efficient and have completely displaced GPUs in crypto, in any kind of crypto functions actually. Not only mining, but even what the government called cryptanalysis.
yeah, I thought you were giving us a trick question there because the folks like Jeff Hawkins, who's been doing hierarchical temporal memory kind of AI, they've been using regular ASICs chips for their entire existence. So from my point of view, it's already happening. It's happened. GPUs, as Axel said in his talk, they happen to be the thing that happened to be
Accidental.
convenient that people are like, oh, this will help me with my neural networks because it kind of works like a neural network. So it was kind of a, oh, yeah, we can do that with that. That makes sense until it gets really hot. And I remember I was running a startup about 10 years ago and I plugged in this new NVIDIA thing that they loaned me. And after a day, I unplugged it because I saw what it did to my PG&E bill. I'm like, oh my God, I can't, I'll go out of business.
Yeah, quick comparison, right? A GPU die is about as big as my thumbnail. Today, they dissipate 960 watts. If you have a gas-powered oven at home, the entire biggest burner on it is at maximum 1200 watt equivalent, right? So right now, we're at a stage where we are burning as much energy and creating as much heat on the area of your thumbnail compared to a burner on your oven, right? Just for shits and grins.
We can say that because
Yes.
it's on the internet.
Yeah, I might just say, so I agree. Thank you. Because, from the math standpoint, to your point, Axel, they needed something that could do vector and tensor math, and GPUs were there. They could already do it because of what they were doing with the graphics processing. But you can come up with a better processor. I mean, Cerebras has done it, but again, not optimized. But again, to the ASIC analogy, we know what we need to do. Somebody just needs to build it and then show it's a lot better than the GPU, which is general purpose.
Correct.
Yeah, so I'm not 100% agree in 5 years. That's probably going to take some time. The reason being the ecosystem and how easy it is now that people can send the job to run on this kind of data center, and it's mostly based on the GPU. So I think the chip, the technology is available, but then to move to all based on new specialized AI chip probably will take some time. That's my view.
Thank you. Thank you, Christian. We have one more here. Thank you.
Thank you. Just making a counterpoint here. Yes, absolutely, somewhat agree with her and want to build on that, right? I mean, the data out there shows there's so much of AI accelerators that are just built every day, and none of them is getting actually used completely. I mean, the GPUs have just reigned supreme simply because of the ecosystem around it, the CUDA that it provides, the fact that it can just take a Python and just merge it together, right? I mean, that's still not there. I'd love to believe that the AI would just take off, just waiting for it to happen, like a normal NPU or whatever.
I agree, and I think what you pointed out is a valid issue because and that goes back to the system thinking, most processor and accelerator designers didn't think about the entire system, meaning including the APIs and the frameworks. So while of course nobody can emulate CUDA directly because it's copyrighted, but most of the real important function calls like matrix multi, so they can be emulated, no big deal. We have an emulation layer that does that, right? Most of the other semiconductor companies that focus on making AI chips, they forgot it or lost the recipe, but we have that in the making, and so therefore we have thought about this. I wouldn't say we solved it yet, but we're getting there.
Could I just, from the debate team comment of why I picked this corner, I just wanted to say, I don't disagree that there might be agreement in 5 years that this is the optimal way to design it, but having come from the commercialization side of analog, devices and FPGAs on the cutting edge and stuff, there's this latency. I mean, I remember trying to get 1,000 customers off of products that were legacy, and so the adoption is what I'm over in this corner for, because there's no way it's going to get adopted in 5 years. But I don't disagree that there might be general agreement that it would be it would be decided that it was an optimal way.
Oh, this is so good. I'm glad that, okay.
All right, guys, is that wrap
This is it?
Okay. Be mindful of time.
Mindful of time, okay.
Oh, we're too late for that.
So it's Stephanie, Axel, and Alex, the dyslexic twins. We're here all week. Tip your waiters.
Thank you very much.
Okay. Thank you, Axel.
Did you get my email?
Yes.
Okay, good. That's is why I sent it to you, plus brought it, because you never know. There it is.
Here we go.
That's me and my PDF. Terrific.
Awesome.
Thank you.
Can I open it with this, or will it be weird? It's going to be weird. Download this. Open this.
Put this away.
Are there panelists for this one too? Yes. Okay, so I'll just put the mic on a chair. Okay.
All right, everybody go.
How you guys doing? Are you still awake?
Yes.
Woo! My type of people.
Is there a way
Some people go to
to?
the club to have fun. We come to learn, right? All right.
Is there a way to like make it?
Yeah, let's do
Still?
full screen.
Yeah, let's do full screen.
No, wrong one. Okay, what is going on right now? There you go. View.
Full screen. Enter full screen.
There you go.
Okay, much better.
Okay.
All right. Let me see. 5:06. All right. So go on until 5:36.
It might be less than that.
Might be less than that.
It's 3.
All right, sounds good. All right, so
Tired.
just real quick, this is the AI Crypto Expo 2-day preview. So if you came here yesterday, you would have seen Fiona Ma, Dr. Ralph Merkle, the inventor of the Merkle tree. You would have seen a lot of amazing people. Also today, a lot of amazing people. So I want to do, so this is only day 2. I want to do a 10-day event, right? I'm doing a 4-day hackathon, 5-day speaker series, 1-day networking. So I just wanted to give you guys like a good little preview of what that means. All right, so I want you all to be involved. We need more speakers. We need more sponsors. We need more vendors. I want it to be a full trade show. But yeah, 10-day event, November 6th and November 15th. You know, this is a 10-day preview. A lot of people have been giving good reviews. So like imagine good reviews times 10. Am I right? All right, let's get it.
We just need times 10 attendees. Or maybe times 100, who knows? Hi, I'm Radhika Iyengar. I'm managing partner of Star Chain Ventures. We're based here. We're backing really stellar US founders who are doing exceptional things with AI and data intelligence. Really focused on traditional industries like finance and healthcare and supply chains. We're excited to be doing some of that, and I'll be showcasing one of the companies we've backed. And it will be an eye-opener, I think, for many in this room, because some of the things that we've been talking about, we will address. A little bit about me. I'm a top 100 women of the future, or one of the top 100 women of the future. Silicon Valley Women of Influence. Spent my whole life in technology. And these days, in the last 7 years, involved a lot in blockchain. I've done a lot in AI. My second company was in AI data intelligence. And so today I'm really looking at the conversions of advanced technologies, and that's really what we're focused on. The enterprise stack, kind of redefining the new enterprise stack with multiple advanced technologies being part of that stack. I guess I'll have to do this manually. Dwayne,
Click
how do I?
click on the second slide.
Oh, I see. Manually do this.
I can.
Oh, good.
You're gonna help.
You wanna, thank you, Preeti. So, yeah, so just, I guess I'll go to that's probably, you can look up my bio online. We'll do this. Okay. Oops,
That looks.
Yeah. So a source of this presentation is a book that I've co-written with my co-founder. Oh, well, that's Dwayne's computer. Is Dwayne around?
I think it's John.
Okay. Can we plug this in? Thank you. You wouldn't want that to die. If not, I have to fly. So it's fine. So this is a source of the presentation, is a book that I've co-authored with my co-founder, Jordan, who's sitting here as well. We wrote a book with a lot of prescience back in 2019 called Enterprise Blockchain Has Arrived. And some of you are quite familiar. In fact, Sunil, you were at the launch of that book in one of the blockchain conferences. So what we are seeing is actually really exciting for us, because many of the things we actually wrote about, which is this convergence of technology, we also wrote about the adoption curve, how this is going to happen. A lot of that was actually written about in our book. Chapter 7 actually laid out the timeline, and we're sitting squarely in that timeline for what we're seeing happening today in blockchain and enterprise, in AI. A lot of what we've predicted is actually happening. So for us, it's really exciting because the things that we wrote about are actually occurring. So yeah, AI in everyday life. I don't know who saw the recent study that was done and published in terms of how people are using AI. It's being used in everyday tasks. Predominant use is in asking, which is there's asking, there's doing, and expressing. I think those are the three major categories. A lot of it is being done in asking. So query, how do I do this? Tell me about this, etc. It's replacing kind of the search engine sort of functionality that we've all come to rely on over the last couple decades, I guess, or whatever, roughly. And then writing, doing things. Mostly it's writing. Jordan and I often laugh at this because we do like doing the writing ourselves. So we don't tend to ask AI to write much. We like expressing ourselves in the way we express. It makes us sound original. That's a refreshing thought, isn't it? But I think that, when we're looking at AI in everyday life, a lot of people using AI in everyday life are not really thinking very much about what is going on behind the scenes. Some of the panels that earlier addressed the question of privacy. Is that data being mined? Who's looking at it? You're really feeding into this big black box that's owned by large enterprise predominantly. And they're seeing all of that data, and it's ingesting all of that data. And a lot of the generative AI means that it's also continually learning on that data too. So, this is a new era of signing away all of your data. I know many have gotten used to signing those EULAs, end user license agreements, and saying, yeah, yes, I want to use your product. And then there was an earlier panel where one of the people on the panel pointed out, we're the product, right? So this is now at a whole new level. And it's a little bit alarming to me because, all of that is going and feeding this giant black box and we don't really understand what's happening. So some of the things that I'm going to talk about today are, can decentralized AI make us safe, right? And we're big proponents of decentralized technologies. Here's some of the ways that AI is being currently used in enterprise, right? Predictive analytics use cases, optimization, productivity. We're seeing that with workflows, with automation, processes in enterprise that are being augmented with AI. Queries, searches, that's along the same lines of personal use. A lot of, tell me how to do this, I want to do that. Tell me about this, I'm looking for this information. Conversation, chatbots, right? Robo-advisors, that's becoming popular. Co-pilots, decision support. And, as we kind of move into more and more use of this technology, sort of ubiquitously, again, questions. What's happening to all of that data? What's going on? Who owns it, right? And one of the things that we actually think about is who owns that? So we're actually big proponents of self-sovereign data. We actually think enterprise is going to be a little bit more leery about doing things out in the open, using these AI chatbots to do various functionalities within enterprise, because again, data has to stay within the firewalls. So we ask a lot of the hard questions on what companies want. Next slide. Because AI is here, and yes, it's here in a big way, but are we really ready? If you look at, in enterprise anyway, 87% of decision makers in enterprise are interested in AI, realize that the adoption of AI is going to be critical to staying competitive in their respective industries, sectors, etc. They realize it's going to be a huge game changer for them. But 85% of those are distrustful of AI, saying AI sounds great, I just don't know if I can trust it, right? Trust is a big word. I mean, the more we've moved into this 100% digital world, and I think COVID and the pandemic accelerated, sort of completely catapulting us into this fully digital world, everything relies on trust. So do we trust? How do we establish trust? How do we get to that point? So if you look at some of the issues in enterprise, I've put up a few. These are some of the big challenges, the hurdles we have to cross. As we think about adoption, we've been talking a lot about how do we adopt this? What's the timeline for adoption? So a lot of that timeline for adoption will be around solving for some of these really, really difficult things, which is safety, alignment, bias, explainability, transparency, cybersecurity. There was a whole panel talking about cybersecurity attack vectors, right? So, as things have gotten more sophisticated, so have the bad actors. They're also adopting the same technology, by the way. So, in fact, one would say that if you look back in the course of history, who are the first and fastest adopters of technology?
Criminals.
Correct. Because they have, creative ways that they're trying to do bad things. And so when the internet was born, some of us were around when that happened. Who remembers when internet was banned in enterprise? Yeah, if you remember those days, you're as old as I am, or a little older than that. So, it was banned because it was considered nefarious, malicious, bad. Lots of bad things happen over there. And it was true, because a lot of the bad actors were adopting the internet and the power of this information superhighway, as it was called, to do bad things. And so enterprise said, oh, no, we don't want that within our firewalls. So a lot of the cybersecurity attack vectors still exist. In fact, they've actually proliferated. I think the lady in the back there talked about connected devices, right? Expansion of attack surfaces, right? So there's the more connected we are, the more devices we are connected to and have this great network we're a part of, the more the attack surfaces have multiplied. So this is a huge thing. Surveillance. Privacy. Somebody talked about robots. I for sure am not ready to have a robot do anything in my home, because all I would want to avoid is some attack happening, somebody malicious taking over said robot and monitoring everything that I'm doing within my home. That privacy is sacrosanct. My sanctuary is my home. And it's like, the best way to think about it is, this is another person. Would you allow another person into your home to do everything for you? Well, it comes down to that lovely word called trust, right? How do you establish trust? And when we hire people to do different things in and around our home, we do trust them to do certain things, right? So how do we establish digital trust? So this is the big question, right? As we move forward in adopting AI in enterprise. Manipulation and misinformation. Well, black box. What's the source? Is it a credible source for information and data? If you don't know what the source is, at least in current search engine sort of mechanisms, you can actually see the source. You can go to the source yourself and say, okay, is this a trustworthy thing? Who are these people who wrote blah, 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 right? Whatever. You can actually verify, validate these sources to some extent on your own. To some extent, it's what you read and say, well, this sounds credible. I guess I believe this, right? Remember the days when we would write, publish papers, write essays? What were we told? Wikipedia was not good for a citation source. Why? Because, you just don't know who wrote it, right? You don't know who these people are. Are they knowledgeable about this topic? Do I trust what they're writing? So this, now this black box comes out and says ABC. Is all of ABC true? Is A true, maybe B not so true? How do you determine, right? On the fly. And yet we're going to be using these on a daily basis. And so we really want to think about, well, misinformation and manipulation, right? Propaganda. It's a new way of establishing propaganda. So source, verification, data, origination, these are things that we actually think about. These are big issues to cross. Data ownership and agency. Who owns my stuff? And this is also, by the way, connected to the next, which is IP and copyright protection. Who's been following all of the lawsuits happening, right? I don't know that the settlements were enough, by the way. $3,000 for an author to say, oh, here's your little piddly compensation because we stole your stuff. That to me doesn't, compute as compensation. This is IP and output, right? So who's responsible for honoring these values that we hold so sacred, which is ownership, originality, content, right? This is my thing that's out there. I get scared. We've been talking to another author, and this author is putting up their entire work, manuscript that they're writing into ChatGPT. I'm horrified when I hear something like that. I'm like, okay, well, you just signed away everything, right? You just offered it up, here, take my firstborn, So we stay awake at night thinking about these kinds of issues. And then the last thing, economic risk inequality. Who has access to this? Is it representative of all of us as a global population? If you thought the digital divide was big enough, this is just expanding it that much further. So, access, equality, democratization, these are actually important values. So, next slide. We think it has a lot to do with the centralization challenges. A lot of this conference has been about blockchain and other technologies that are offering an alternative architecture, an alternative path to how we address some of these challenges. Think of centralization having a number of these issues. I won't read through all of them, but we are looking at privacy, we're looking at of data, we're looking at bias and lack of alignment. And then we call it a single point of failure because in a centralized system, there's one owner, one entity that owns everything. It could be distributed, which is different from decentralized. Distributed just means that there's one owner and it's distributed in multiple locations. Think of data centers, for example. There may be one entity, large entity, that owns all these data centers. These data centers can exist all over the world, but they're essentially distributed. But it's not decentralized because it's still one owner. In decentralization, you truly have multiple owners. And this is something that's going to be incredibly important as we go forward because it's harder to do the attacks all at the same time for a majority of these owners in a network simultaneously, right? Just harder to do. Not impossible, but harder to do because it's really about who's going to be colluding on these networks and can they collude all at the same time in a sufficient majority in order to be able to attack the entire system. And so this is, again, this is like law enforcement. Why do laws exist? Not to prevent, but to deter, right? Laws exist to protect us because supposedly the punishment or the consequences of committing that crime are great enough to say, God, I don't know that it's such a good idea for me to do this bad thing because I might end up really, suffering, right? So that there's a certain level of deterrence. So what we're looking at is how do we establish the right systems for the future with the right levels of deterrence embedded in these systems so that we have a bigger hurdle to cross to commit the crime. We're not saying the crime cannot happen because that's part of, I think, nefarious activity. People who want to do bad things will continue to do bad things. But can you develop the right kinds of systems with guardrails, frameworks, fail-safe kind of mechanisms? What kind of systemic kinds of systemic frameworks and guardrails can we establish to help us safeguard the things that we want to safeguard? Next. Well, back to that word, trust. That's the big T word. So enterprises and people, these are things that we actually hold pretty dear. Security, privacy, confidentiality, compliance, identity, who owns my stuff, governance, right? These are all things that we should be caring about when we look at the role that technology plays within society. So we can either have technology work for us or against us. We'd like to think that technology actually can work for us. Next. So in comes what we call a decentralized AI. This is an AI that is system that is built on a decentralized framework, which means that it can be verified and authenticated. So remember when I said that there will be multiple owners? So think of a network. And think of a network like in this room. Let's say we were all nodes on the network, and we each own our own network. We own the data, we own everything in our own networks, and each of us is a node on this network. If you or anybody wants to do business with me, I have to declare my identity. I have to verify, I have to authenticate. You can actually see where it's originating from. The entire network is, by the way, transparent. So you can see what I'm doing, I can see what you're doing. We all can kind of see, to a certain extent, in a shared data sort of context. And again, I'm not going to get too technical in this, but we all have to kind of agree the minimum level of information that we're going to share about things. And certainly in enterprise, there's a lot of KYC and AML that has to occur with every node on the network so that every other node can say, is this a worthy participant in this network, right? So it's all about being verified and authenticated. It is aligned for values because, by the way, it's incentivized for honesty. We all have a role to play. And the more we play, again, with the system rules and say, okay, we're going to incentivize this for honesty, that means that if somebody is being dishonest, let's say I'm being dishonest, any of you can call me out and say, well, we're seeing some interesting, unpredictable, aberrant behavior coming out from this network, me, and we need to investigate this. And again, this comes down to governance rules. There are rules in every network that get developed, and we have to abide by rules, kind of like society. We have laws, we have rules, we have regulations, and we should try to abide by those regulations when we're operating for business. Incentivized for truth, like I said. Open source, again, not a new concept. We've known about open source for a really long time, but open source just means that there's no black box. We kind of get to build on things together. We kind of get to collaborate and coordinate with one another, and that's largely reliant on open source, which prevents the whole black box scenario. Ownership of data, we talked a little bit about that, so I won't talk about it more. I wanted to give a little spotlight on a company that we're backing called ZeroG.ai. It's pretty exciting because what they've developed is a complete system, decentralized compute, decentralized storage, fully decentralized capabilities that are designed for enterprise. The beautiful thing is that it's 95% cheaper and it's 10x faster. So those of us who have wondered, gosh, is this the holy grail? Will we actually be able to create a system that is extraordinary and that is capable of handling the type of compute capacity that enterprise needs, the kind of storage that enterprise needs? Can we create a system like this? We happen to think that ZeroG.ai has that kind of system. It is in still earlier days, I will say that. So it's going to take maybe another 3-4 years, maybe sooner than that if we're lucky, before it's actually something that is ready for prime time. But on the testnet, it has been extraordinarily performant. So it's fast, it's proven to be cheaper, so much so that there's a whole Forbes article, you can check it out. It's written by Sandy Carter. Basically, you think of it this way. It's a new model where it's been proven, at least in test parameters, that it has provided a system or a backdrop in which enterprises or anybody can run training for their LLMs. It's over 107 billion parameter model that is enabling enterprise to train on this. It's fully decentralized, which means there's alignment nodes built into Zero-G, which means that every node really can look at all the other nodes. Remember I talked about accountability. This is about accountability. So if I'm the bad actor in the network, all of you can call me out and say, we see some stuff happening through this node that's not really good, right? And so this alignment helps us stay more true, stay honest in terms of how we're going to conduct business. And all of the nodes really have this capability of being alignment nodes and validator nodes in this network. The other good thing is that it's been proven, at least in testnet mode, that it can run on 1 gigabit per second network. So those, you think about enterprise needs to be able to run this on a very large, fast network. Well, it is fast, but it's not so large, right? So it's a pretty incredible engineering feat from that standpoint, that this system that they're developing, this protocol, it's the largest layer 1 that has been created. It's very exciting stuff. They're just getting ready for prime time, so to speak. But we happen to think that they're approaching it in a way that is prioritizing the things that enterprise cares about, which is scalability and performance, but not sacrificing the values we all should be caring about, which is honesty, transparency, alignment. And why are they doing all of this? Because they actually see a big future in having the right rails for humanity. So, thank you. So I just wanted to conclude and say that really at the heart of all of this is thinking about what systems are we going to build for the future. I happen to think that it's worthy if we're building it for all, that we're building it to be inclusive at the foundation, that we're building it to be enduring, not transactional, and that we're certainly building it to be beneficial, not malicious. So we actually happen to think that supporting companies, backing companies that are building things that are delivering the values without sacrificing technical competence and performance, which are of course very, very important. In order for all of us to be able to adopt and use these systems in tomorrow, we absolutely have to think, but let's not sacrifice the values that we care about while we're doing this. Thank you.
Panel, please come up.
Yeah, I don't think we need it.